Hey guys, good evening, morning or afternoon. So this video will be talking about optimization. Okay, all right. Okay, so optimization, right? And which would be the last part of our functions and derivatives, right? Chapter that we'll be covering. So optimization, actually, it's more about a real world use of derivatives. Okay, one of the real world uses of derivatives. Uses of derivatives in engineering context. Okay, in engineering. Okay, and there will be a couple of things that we'll be covering in optimization before we actually go and look at some problems. The first we want to cover is about the higher order of derivatives. Okay, so higher order of derivatives, and then we're also going to talk a little bit about maximizing actually rather, or maximum or maximizing, whichever you prefer. Okay, minimizing, right, when you're talking about maximizing or minimizing something, and also a little bit about inflection. Okay, inflection itself. So I'm just going to put a bracket here, maximum or maximizing, and minimum or minimizing. Okay, they are very similar but not the same thing, by the way, because of course one is a noun, right? Of course maximum and minimum are nouns, right? And you know, right, that's noun, right? You put as n for noun, and of course maximizing and minimizing are verbs. Okay, but they are related, and inflection also. So this is talking more a little bit about functions itself. Okay, when we're differentiating functions at fx. Okay, so we'll go very briefly through each and all of them before we jump into some optimization problems. So not to fret, not to worry. So let's move on. Okay, so okay, so when you talk about higher order of derivatives, okay, so when we talks about what is a higher order of derivatives, okay, higher order of derivatives, right? Normally in most scenarios or most cases, we are asked to find dy over dx, right? Normally we know how to find dy over dx, or we're asked to find dy over dx in many contexts. But sometimes, okay, we need to know about d square y dx square, okay, or d cube y dx cube. Okay, we need to know these cases. And what I just mentioned right here is what we call as a second order derivative. Okay, so this is obviously what we call a second order. Okay, and this is what we call as third order. D cube y dx cube is what we call as third order. Okay, third order of derivatives, right? And they are useful in many cases actually, but for our focus, usually second order of derivatives is what we're really interested in mostly. And yeah, let me enlighten you with a real example. Okay, a very common example that you might see in terms of motion regarding the second order derivatives. Okay, right, okay, let me draw a graph. I'm going to use white, I think. So let's say we have a graph here. Okay, you probably have seen this in physics. Okay, this is what we call as our what graph we call this? S versus T graph. Okay, so S, as we know and we study in physics, actually is what we call a displacement graph. Okay, displacement versus time graph. Okay, displacement versus time. So displacement, actually, it's not exactly the same as distance, right? Displacement, remember the difference is that it's basically talking about position. Okay, it's more about the position of an object from its origin, from its origin, okay, its starting point, or origin as I like to call it. So when we are talking about a displacement graph, let's say for example, maybe your graph would look will start from the origin, okay, and maybe the object is moving something like this, right? This is the path, for instance, okay, so it looks a bit interesting, okay. Just pretend this is an example, okay, and this displacement versus time graph, okay, we can write it like this as s is equals to a function of time. So that means to say that the object's position is a function of time, okay. Object's position is a function of time. Object's position is a function of time. Right? And normally when we take the first derivative, okay, let's say for example at this particular point here, okay, curiously we take at this point here, and we're gonna call this as t1, okay, and we're gonna call it as s1, okay. Right, let's say if I take a point right here, I draw a tangent line, okay, I take a point right here. This is what we call as our first derivative, yeah, ds over dt, okay, first order derivative in this case, okay, and it's a line that's tangential to the curve itself, okay, and this ds dt, normally in any phenomena we would call it as the object's velocity, okay. We're talking about the velocity specifically at t1, okay. So first order derivative would get us the velocity. So the velocity is like the speed, but again it's more about it's also referring to its direction as well, right? It's also referring to its direction. Where is the direction from origin? So where is it going? Like, is it going towards or away from the origin point? And of course, and its speed, right? That's the meaning of velocity, okay. So you don't need to be wondering a lot about this for the time being. I just wanted to show you a real example. So this is velocity, and velocity normally is what we treat it as a first order derivative. It's called first order. Now if you're interested in, let's say, the rate of velocity, okay, if you're interested in the rate of velocity, for instance, so let me just draw a small graph right here. Just pretend I draw a small graph here. This is t, okay, this is v, and maybe for example, well, let's just say that the graph is sort of well, going like this, for example, okay, and just pretend that this is t1, okay, this is t1 maybe, okay. This is just very arbitrary, yeah. There's no specific values to it, and we take the derivative of t1. So I'm going to draw this with a, again, a blue line, okay. So it's tangential to the graph itself, okay. This is of course v1, right? We're going to do v1. So this line here, okay, will represent dv dt, right? dv dt, the derivative of velocity with respect to time, or the second order derivative of displacement, d squared s over dt squared. Alright, so this is actually what we call as a second order derivative, okay, a second order derivative. And normally the phenomena that's used to represent here is acceleration, okay, it's acceleration. Okay, so this is basically one real world use of higher order derivatives. We can easily study the displacement, okay, we can easily study displacement and its relationship of displacement with you know, velocity, right, and acceleration, right? We can study velocity and of course with acceleration. Okay, which is obviously displacement to velocity is just simply ds over dt, and displacement to acceleration is d square s over dt squared, which is second order derivative. Again, there are many cases where we'll be using derivatives of higher order, but one popular example is the one I've just highlighted in the graph below. And don't panic about the lines I just draw on top of it, the tangential lines. Okay, this one I will explain later in this video. Okay, what do these tangential lines mean? Alright, so without going further astray, let's show some examples of how to find the second order derivative of functions. Okay, okay, alright, so if it's for a normal function, okay, that imagine that our fx was just maybe let's just say ln of x times sine x, okay, and the question wants us to find the second order derivative. Okay, the question just wants us to find the second order derivative. How are we going to do that? So first we're going to find the first order derivative, which is just simply dfx over dx, or in other words we write it in notation f prime x. So quite simply the product rule, you know, you just simply take your u and then you take your v, okay, and then you know it's just simply v du dx, okay, and plus with u dv dx, right? So frankly speaking, it's very straightforward. So it's just simply sine x, du dx is just 1 over x, okay, so over x plus u ln x times the cosine of x, okay. So yeah, that's basically your first order derivative. Now if you want to find your second order derivative for such a function like this, so d square fx over dx squared, or in other words f double prime x, okay, so you know we have to do some product rule and some quotient rule, because the first function here actually involves a little bit of quotient rule. Okay, so this one involves a little bit of quotient rule that we discussed in the previous videos, like I think the earliest video, and this one of course will involve a bit of sine rule here. Okay, so this will involve a little bit of sine rule, not sine rule, sorry. My bad, I mean to say product rule actually, right? Product rule. Okay, so upon differentiating each of the functions individually, so you get here v du dx is cosine of x minus u dv dx, which is just 1 over v square plus v du dx plus u dv dx. Okay, so you can leave it like this, okay, or if you want to simplify it further, be my guest and go ahead and simplify it. There's no problem at all whatsoever, as long as you know how to get from the first derivative to the second derivative. That's all that's important, alright? And that's all and well for normal functions, right? And even if the function is a little bit complex, also it shouldn't be that bad. Let's say the function involved, I don't know, maybe a hyperbolic function like sine h, for instance. Okay, you just, you know, use the basic differentiation rules and try to approach this problem. But how about if we're dealing with a different kind of function, okay? The one we discussed in the last video, such as a parametric function. How do we find the second order derivative of such a function? Okay, so let's give an example. Okay, so let's see here. Okay, let's say for example, okay, let me erase this by the way. Okay, so we say that we have a function of x equals to t squared and y equals to 1 over t. We want to find du square y dx square, right? We want to find the second derivative, and this is a parametric function. So how are you going to do it? Well, quite frankly, we of course find the dy dx, the first derivative, right? First order derivative, which is just simply dy over dt times dt over dx, and we know that dt over dx is just simply times with, well, 1 over dx dt, right? So that's the idea itself. So dy over dt is just simply negative 1 over t squared. If that makes sense, yeah. Negative 1 over t squared, and times with 1 over dx dt is just simply 2t. So in this case, it would be negative 1 over 2t cube. Okay, so this is your dy dx. Now if you want to find your d square y over dx square, it's just simply d over dx times dy over dx, and you can write it like this as d over dt. Okay, we're going to express in terms of t, dy over dx times with dx, alright, dt over dx. Okay, so times with dt over dx. Okay, which in this case would be d over dt times dy over dx, and you can write it as dx over dt. So in this case, it's pretty straightforward. So dy over dx. So how are you going to differentiate this? We can simply write this as negative half t to the power of negative 3 to make your life simpler. So we would have 3 over 2 t to the power of negative 4, okay, over dx dt, which is just simply 2t, right? So it becomes 3 over 2 t to the power of negative 4 times 1 over 2 to the power t to the power of negative 1. So it becomes 3 over 4 t to the power of negative 5, or it's just simply 3 over 4 t to the power of 5. Okay, so this is basically finding the second order derivative for parametric functions. Now how about for implicit functions? Okay, now this is a bit interesting. Let's give a simple straightforward example of one. All right. Okay. For implicit function, let's say we are given a function of x squared plus y cubed, okay, minus y plus x equals to 0, and we are asked to find d square y over dx square. So how are you going to find it? Of course, we first differentiate the left and right hand side. So this will be our LHS, left hand side, and of course I'm gonna put it as RHS, which is our right hand side. Okay, and if you want to put an S here. Okay, so we're gonna differentiate both sides, okay, with respect to the derivative d over dx, right? And of course right hand side we're going to also differentiate with d over dx. Okay, so as we do this, we have 2x plus 3y squared dy over dx, okay, minus dy over dx plus 1 equals to 0. Okay, so the first step we do is obviously try to rearrange it to find dy over dx. So dy over dx is equals to 3y squared minus 1 equals to negative 1 minus 2x. Therefore dy over dx is equals to negative 1 minus 2x over 3y squared minus 1. So I'm going to write it right here just to save space. So dy over dx is just negative 1 minus 2x over 3y square minus 1. Okay, so with that side we're gonna erase this. Okay, and what we're gonna do is, of course, we're gonna rearrange this a little bit, this intermediate step. So we'll have here 2x plus 1 plus 3y square minus 1 times dy over dx equals to 0. Okay, this is our intermediate step. And again, we're gonna differentiate the left hand side of the function here. Okay, LHS. Okay, we're gonna differentiate the LHS with respect to d over dx, and of course we're gonna differentiate the right hand side, of course, with respect to d over dx as well for the right hand side. Okay, so as we differentiate it, okay, what happens is we're gonna get 2. Okay, of course 1 will be out of the equation, and this part right here will actually undergo the product rule. Okay, this part is going to undergo the product rule, by the way. So this will be undergoing the product rule. Okay, so yeah, we're going to, of course, differentiate the product rule. So therefore, you know, we'd have here dy over dx times 3 square y will become 6y in this case. Again, don't forget we have a dy over dx, okay, plus 3y square minus 1, okay, and we're going to take a different derivative, it will become d square y over dx square, and yeah, that would be it. It will be equal to 0. Okay, so one thing I'd like to clarify is that, let's say for example you have here 2 dy over dx. Okay, so that would mean what? That would mean that once we, of course, go back to the original equation, become 2 plus 6y dy over dx squared plus 3y squared minus 1 d square y over dx squared equals to 0. Okay, so basically the dy dx will end up having a square, so dy or dx squared. Okay, and by the way, dy over dx, the whole thing squared, is not equal to d square y over dx squared. So be careful of this. Make sure you do not simply think that, okay, dy over dx, the whole thing squared, is equal to that. No, it's not equal at all. Okay, so this one must remember. So this one you have to remember that. Okay. Okay, so in this case, I just wanted you guys to remind you guys of that. So without further ado, okay, running out a bit of space actually, but hopefully it won't be a problem. Not gonna take my pens. Right, so what we end up having is 3y square minus 1 d square y and dx square is equals to negative 2 minus 6y dy over dx squared. So dy over dx we already got earlier. Okay, I'm just gonna put it here. So negative 1 minus 2x over 3y squared minus 1, and therefore d square y dx square is just basically 1 over 3y squared minus 1 multiplied with negative 2 minus 6y negative 1 minus 2x over 3y squared minus 1. Okay, don't forget the squared, by the way. I almost forgot the squared actually. Alright, squared. And this is your final answer. I know it's a little bit scuffed, but if you can have the time to simplify it, go ahead and feel free to do so. But this is basically the approach when it comes for implicit functions. So hopefully that was clear. Now we'll be proceeding to talk about maximizing, minimizing, or maximum, minimum, and inflection points. Okay, so let's go back to that now. Okay, so we're talking about maximum, minimum, and inflection. Okay, so these three things: maximum, minimum, and inflection. Okay, so let me try to draw a graph here. Okay, which is axis. Okay, we're gonna draw x versus y. Okay, and I'm gonna draw a curve that would look something like this. Okay, so when we have a curve, okay, and let's mark a point here. This is point. I'm gonna mark this as, okay, x1, and I'm gonna mark this as y1, and of course we'll mark a point right here, x2, and I'm gonna mark this arbitrary point, of course, okay, apologies for the writing, as y2. Okay, so let's have one last point. Let's mark that as x3. Okay, y3. Okay, great. So let's talk about these 3 points first of all, first and foremost. So what we notice is that when we take a derivative of a function, okay, so for example, we can say this is a function of y equals to fx, and we take the first order derivative of it. Okay, so we try to take the first order derivative. So we'd have here dy, oh sorry, oops, that was a weird writing of dy, my apologies. So I made it a little bit smaller, but okay. So we would have dy over dx is equals to f prime x. So we take the first order derivative. What happens in a graph is we end up getting a tangent line. Okay, a tangent line at that point. Okay, at x equals to whatever point you want to put. Let's just call this point as a, for instance. Okay, a could be any point. So for these 3 points, let me draw the respective tangent lines. Let's use gray. Can we use gray? No, actually let's use different color. I was thinking of red. Okay, so for the first one, if I were to draw the tangent line, it would look something like this. Okay, so that is for f prime x1. Okay, and for the second one, right, let me choose a different color. Okay, so this, oh wow, it's not that great. Let's use pink. Okay, hopefully it's clearer now. Okay, much better. So that is our f prime x2. And if I want to use a slightly different color, let's use for, I'll just use, no, green. Let's use yellow. Okay. And this is a tangent line at, okay, let's pretend it's a tangent line. No, it didn't touch properly. Let me draw it properly. So it touched the point. Okay, yay, hooray. So that's your f x3, right? It's your derivatives, your first order derivatives. Now you might be surprised to learn that actually fx prime 1 would be equal to 0. Okay, once you do the derivative, you plug in the x1 value to the derivative function, you end up getting 0. And also likewise for fx prime 2 would be equal to 0. And why is that the case? Is, well, your fx1 prime is something which, okay, it's not the same colored red I was looking for, but it's a little bit more, okay, yes. I know the color red's been changing a bit, but I hope you can bear with me this one. So this is what we call as our maximum. Okay, more so we call it our local maximum point. Okay, and f2, okay, fx prime 2 is 0, is what we call as our local minimum. Okay, your local minimum. All right, and basically f3 prime actually, okay, you'll notice that it's obviously clearly negative, right? It's going in a negative direction. Okay, And we're not going to talk about fx3 prime for now, but let's talk about fx prime 1, fx prime 2. So what is the local maximum actually? What I'm trying to say is that when this point is a local maximum, it is basically the maximum value, right? So meaning to say that it will generate the maximum value, meaning to say fx1 will generate a maximum value. So y1 is actually the largest value in the function itself. But I put the word local because there might be other maximums. Okay, there might be more than one maximum in this function. We do not know how many maximum does this function have. And one of the ways to actually find the number of maximums of the function is to find whether f prime x is equals to 0. Okay, then obviously you'll have many answers, and of course one of them will involve x1, x2, and maybe any other values we don't really know. And likewise, f prime x2 equals 0, so x2 is technically the local minimum, because that means to say that fx2 will get you the smallest value out there. And it's local because, again, we also do not know how many minimums can we get in the function. Okay? And this is a very important thing actually to keep in mind, right? And if you want to know actually further whether it's a local maximum or local minimum, if you want to double check, because maybe once you try to find when f prime x equals 0 and you get x1 and x2, you don't know whether they're maximum or minimum. You won't know whether it's maximum or whether it's minimum in this case, right? You wouldn't know at all. So how would you figure that out? Is actually through the second derivative, right? So if you were to find d square y dx square is equals to, of course, f double prime x, okay, this will allow you to tell whether it is a maximum or minimum. Okay, a maximum or minimum more clearly. Okay, previously what we found was the first derivative is equating to 0. It actually means a stationary point. Okay, it means a stationary point. Okay, stationary point, or in other words, sometimes you might be familiar with this turning point terminology that we've learned in high school. Okay, this is also the pink one as well. Okay, where is it? The pink one here, also the same thing, right? It's also a stationary point or it's a turning point. But if you want to know whether something's a maximum or minimum, we take the second derivative, which will either let us know to know if it's a maximum or minimum. If it's a maximum, that means your second derivative, okay, in this case our f double prime x x1 will become less than 0. That means it will be negative. And our f double prime x2 would become greater than 0, or it's positive. That we'll know that it's a minimum or maximum. Okay, so that is basically the idea for identifying minimum and maximum. And sometimes this is very important in maximization and minimization problems, where you want to find maybe like the minimum value, where you want to find the maximum value, right? So this is where we might need to use our knowledge of the first derivative, where we want to make sure it's equal to 0. And the second derivative, if it's a minimum, it must be greater than 0. If it's a maximum, it must be less than 0. Okay? Okay, since that's good, now we'll talk about the third thing, which is the inflection point, which I've highlighted in yellow. So you can see that f prime x3 is negative. How do I know it's negative? Because one thing about the derivative, alright, it's a tangent line, yes, but it also acts as a gradient. Okay, it acts as a gradient at a point at x equals to a. It's the gradient of that particular tangent line, right? And we know very well that for x is 1, okay, can I use yellow? I keep on conflating the colors too much. Okay, so we're going to use yellow. So you see, we know that its gradient is 0 because it's a flat horizontal line, right? Once you draw the tangent line at x1 and x2, you can clearly see the flat line itself. But for x3, when you do the first derivative, it's not a flat line at all. It's actually negative because we know it's sloping downwards, right? So that's the thing about x3. It's negative. It's sloping downwards actually. Okay, but one thing to note is that if we take the second order derivative of x3, f prime x3, and we get a 0, okay, in this case if we probably do get a 0, what does it mean is that the graph is actually changing, is actually moving from min to max. Okay, so f prime x3, if it equals to 0, graph is changing from max to min, okay, or vice versa, whichever way, it doesn't matter, or min to max, right? And this x3 is what we call as a inflection point. Okay, basically inflection point doesn't serve much, I would say. I wouldn't say much, but not as much as maximum minimum in the optimization problem. It's just a point that we know where the graph changes from maximum to minimum or minimum to maximum itself. Okay, so in order to quantify for inflection, we must know that the double derivative of that point has to be equals to 0, and whether the first derivative is, let's say, less than 0 or not less than 0, let's say it's more than 0, for instance. Okay, I don't have much space, unfortunately, so let's say less than 0 or more than 0, or even if it's equal to 0, even if it's stationary point, even if it's a stationary point, it don't matter. Okay, as long as the second derivative is equal to 0, then we know that x3 is an inflection. Okay, and if you, let's say for example, x3 was 0, like the derivative of x3 was 0, what would happen is that this would, of course we'll have the line like this, and this would be called as the stationary point inflection, right? So this will be a stationary line, stationary point of inflection. Okay, so I know the board's a little bit messy, but hopefully you get the idea. Actually, for maximum, for minimum, and inflection point, what are they essentially? Okay, so to summarize, let me just read all of this real quick, because I think this is already getting a bit messy. Okay, to summarize, okay, if let's say we have a point where f prime of x is equal to 0 and f double prime of x is greater than 0, it is a minimum. Okay, it is a minimum, the minimum point. It is a minimum point. If we have the case of f prime x is equals to 0 and f double prime x is less than 0, it is a maximum point. It is a maximum. Okay, and last but not the least, if we have, for example, f double prime x equals to 0, regardless of f prime x value, it is an inflection point. Okay, it is an inflection. Inflection point. Okay, so inflection, because we are involving the change of maximum minimum. All right, and hopefully they get the idea behind that. Just one more last thing I'd like to clarify with you guys before we move on to the problems. I know this is quite a big chapter because we have a lot of things to cover, but just one last tiny thing I just want to mention. Yes, so let's go back to the graph that we talked about earlier. Okay, I'll pretend we plot x and we plot y. Okay, and let's say I draw this graph again. Okay, so multiple, minimum, maximum. Okay, so if I were to take the tangent lines for all these points, okay, so this is a tangent line here, and this is a tangent line here. Alright, so also one more thing as well, we have another inflection point. Okay, so I'm going to write here A, B, C, D, E. Okay, so what is A? A actually, as we know, is a local maximum, right? Local maximum. B is a inflection point, clearly is an inflection point itself. Okay, C is clearly a local minimum. D is a inflection, right? And F is what we call as a absolute maximum. Okay, so you see why I wanted to bring your attention is to talk about the difference between absolute versus local. What's the difference between these two? Okay, so the thing is that absolute, by the way, yes, absolute is basically the largest or the smallest. If we're talking about absolute maximum, then we talk about the largest or smallest in the entire function. In the entire function, okay? Function. But local is just basically large or small points. And of course, there are stationary points too, okay? So when you say a point is local, so there are stationary points. Absolute are also stationary, by the way, okay? Absolute, of course, you can clearly tell the stationary points. And what do you mean by stationary points, okay? Again, it's just to say that your dy over dx is equal to 0, and that's why you would end up having a flat tangential line, okay? A flat tangential line means that your gradient of the tangential line is 0, and that's why it's a stationary point, okay? So that's the difference between absolute and local. So in case if someone say what is an absolute point, what's a local point, absolute is usually the largest or smallest stationary point in the entire function, whereas local are usually large or small stationary points in the function itself. Doesn't mean that they're the largest or the smallest value. And of course, y, b, and d are inflection points because, as I mentioned earlier, okay, their d square y over dx square is equals to 0. The second order derivative is equals to 0, whereas for a, we know the second order derivative is not equal to 0. It's actually greater than 0. Sorry, yeah, it's not greater than 0. It's actually less than 0, I'd say. Oops, sorry, let me use the other eraser. It's actually, as we discussed earlier, it's actually less than 0, it's negative. Whereas for the minimum, the d square y dx square is positive. So you see the change from negative second derivative to positive second derivative, right? And the point responsible for that, okay, which lies at d square y dx square equals 0, is what we call as the inflection point. Okay, so hopefully that's a clarification of these three things. Alright, maximum, minimum, inflection, and we talked about higher derivatives. Now let's look at some problems actually. Let's try to solve some problems together before we wrap up this tutorial video. Okay, let me look at some questions first from the book. Okay, alright. So, first question, they gave us the value of fx, okay, and it's given to be x cubed, okay, plus 6x squared minus 15x plus 51, okay, and they want us to of course find the stationary values. So they want to know what the stationary values, right? And they want to know the stationary values. Okay, that means to say they wanted to know whether there's any maximum, minimum, okay? They want to know this, and also they want to find inflection points as well, okay? If there's any inflection points or not. Inflection points, and thus they want you to sketch the graph, give a rough sketch actually. Okay, they want you to sketch the graph. Okay, so I will let you guys have the opportunity to pause the video before we try out this problem. Okay, so okay, So assuming that you guys have paused this video and give it a try, so let's actually try to solve this problem real quick. Okay, the first thing to do is of course find the first order derivative of this function. It's pretty straightforward. It's just simply 3x squared plus 12x minus 15, and the second derivative, which is just 6x plus 12. Okay, so if you want to find the stationary point, okay, the stationary point is pretty straightforward. Okay, stationary, I always spell the word stationary points wrong. Okay, so stationary points, it's pretty straightforward, really. It's just, well, we get f prime x is equals to 0, and we know that 3x squared plus 12x minus 15 is equals to 0. Then of course we'll be able to get two values, okay, which is x1 is equals to, if we were to use our calculator, and of course we'll find x2 as well, surely. Alright, you can use a calculator or any quadratic formula techniques to solve the problem, but I'm just gonna stick to the calculator for the sake of time and simplicity. So yeah, degree 2 is 3, 12, negative 15. So yeah, we get 2 points. We get x is 1, okay, x1 is 1, and y1 must be something else, which we'll find in a while, and x2 is negative 5, and y2 is what in this case. Okay, so with that being said, we have to find the $43. Okay, and y2 would be 151. Okay, so yeah, and also one more thing is that I want to find the inflection point at f double prime x1. How much is it? Is it positive or is it negative? So in this case, 6(1) plus 12 would be positive. Okay, so therefore we know that this is clearly a minimum point, right, which is a very important thing to note down. So this is a minimum point. Okay, and if we do f double prime x is 2, which will obviously give me 6 times negative 5 plus 151, which is 120, plus 12, my bad, sorry, would give me negative 18. Okay, since I get negative 18, then I know clearly that it's less than 0, so therefore this would give me a maximum point, right? This is going to be a very large point, it's going to be a max point. Now, of course, we want to find the inflection point here, so I'm going to erase this, and to find the inflection point, we know that, oh, oops, I'm using the wrong color. Okay, to find the inflection point, okay, what we know is that f double prime x is equals to 0. So 6x plus 12 is equals to 0, 6x equals to negative 12, x is equals to negative 2, and therefore your y would be equals to x cubed plus 6x squared minus 15x plus 51, calc negative 2, 97. Okay, so this is our inflection point. Okay, this is what we call as our inflection point. I'm going to highlight this in orange. So this is what we call as our inflection point. Okay, so once we have found our maximum, minimum, and inflection points, the next step to obviously do is to sketch the graph. So I'm going to of course erase this for a bit. Okay, sketch our graph. Okay, can erase this for a little bit. Okay, because we already got all our points already, so we can actually scratch off the stuff that we already need. In this case, if we draw the graph, oops, sorry, I need to erase this a little bit. Okay, if we draw a graph, okay, Alright, this is our y, this is our x. Okay, remember also the y-axis goes down. So you'll have your first y-axis, your first coordinate here, -5, and then your inflection point at -2, and your minimum point at 1. So of course at 5 would be 151, okay, 97 and 43. Okay, so I'm gonna plot my first point here, okay, as a sketch. Alright, and then second point also, and third point. Okay, so once I'm done plotting the points, eventually the individual points, so what's gonna happen is I'm gonna sketch the graph. So we know that it's a local maximum, so look like this, and then it will hit like this, and so on. Okay, it's a very rough sketch, but you can see that as we pointed earlier, that this is our max, right? This is our maximum, right? A local maximum, and this is our local minimum, right? And this is our inflection. Okay, so this is normally what you expected to do. Okay, it's pretty straightforward. You don't have to draw an exact graph. You just need to know only the maximum, the minimum, and of course the inflection, and then eventually you'll be able to draw the graph. Okay, so let's proceed to another type of question right here. So let's go to the next question. Okay. Let's see. Let's say we have a question right here, okay, of fx, okay, is equals to x squared times e to the power of -x, and again they of course want you to find stationary points, stationary points, inflection points if any exist, inflection points, and plot the graph. Plot the graph, basically sketch. Alright, so they want you to sketch the graph actually, so it's more of a sketch. Okay, so I'll give you some time, guys, for you to pause and actually try to attempt this question, and later I will try to help you guys out. Okay, so assuming that you guys have tried to attempt this question, the first thing we do of course is to find the first order derivatives, right, and the second order derivatives. The first order derivatives, you know, you have to use a bit of product rule, right? So you have to make your u, and of course you have to find your v. Okay, so I'm just gonna do it real quick. So it's just gonna be v e to the power of -x, and u is just 2x plus x squared, okay, and negative e to the power of -x, right? You differentiate it because e to the power of -x is equal to -x, and then you take out the x, you get negative, right? -1. So yeah, so this is your first derivative. Then for your second derivative, it's gonna look something like this. It's just gonna be, of course, you have to use a product rule, so it's just 2, you know, wow, okay, so 2 itself is x to the power of e to the -x. It would be v, so v e to the power of -x times 1 plus x. Okay, that's how it is. Plus again x squared e to the power of -x would be actually let me put a negative sign out, it will be much easier that way. So we're gonna have negative, okay, bracket x squared of ex, which is just gonna be e to the power of -x times du dx, which is just simply 2x, right? Plus, what was it again? X squared and negative e to the power of -x. Okay, so there's a lot of repetitions actually, which I think got me a little bit frustrated, but yeah, it should be fine. You can simplify it to become 2e to the power of -x minus 2x e to the power of negative x minus 2x e to the power of negative x and minus x squared. So minus minus becomes, well, plus, so it becomes plus actually eventually, because minus and minus would be plus, right? So it become plus, right? So plus x squared e to the power of negative x. Okay, so we already found f prime x, f prime x, f double prime x. So of course we want to find stationary points. To find stationary points, actually, we just have to equate f prime x is equals to 0. So in this case, 2x e to the power of negative x plus minus x squared e to the power of negative x is equals to 0. So to rearrange the function, we would end up having what? We'd end up having 2x e to the power of negative x is equals to x squared to the power of e to the power of negative x, right? So we can obviously factor out the e to the power of negative x, right? It just becomes 1, and then x squared divided by x would be what? We just end up having an x here, right, at the end of the day. So we already have one answer, which is obviously going to be 2 equals to x. That's one answer. But how about the second answer? The second answer would be like this. We would have here e to the power of negative x, well, times x really, is just equals to 2 minus x equals to 0. Okay? And then we can just get rid of it. We'll have here x e to the power of negative x is equals to 0, right? Of course, you know, we would have x e to the power of x equals to 0, and the only option for this to be true is if x is 0. Okay, so we actually have two answers. X is 0 and x is 2 stationary points really. So x1 is 2, then y1 would be what? So it would just be 2 squared times e to the power of negative 2. Sorry, oops, e to the power of negative 2. Okay, so it'll be just 4e to the power of negative 2, right? We're going to leave it as 4e to the power of negative 2. And where x2 is 0, of course, y2 would be definitely be 0 in this case, right? So, rightfully so, we've already found our two stationary points, which is 2 and 4e to the power of negative 2, and the origin itself, which is 0, 0. Okay, so now we're gonna find the second order derivative, right? We want to see which one is maximum, which one is minimum. So I'm gonna erase this real quick. So for f double prime 0, what will be the answer? So that will be 2 e to the power of negative 0. Yeah, it'll just be 2 technically, right? Because everything else will be 0. So that, oops, sorry, what was that supposed to be? Sorry. So it's supposed to be 2. So this is obviously gonna be a minimum, right? And we know that f prime 2 would give me what? Would give me 2 minus 2 times 2 minus 2 times 2 plus 2 squared. How much should that be? Negative here. So I'll end up having a negative 2, which will obviously give me a maximum. Okay, so there's already some information we know, right? This is our max and this is our min. Okay, now if you want to find the inflection points, right, gonna be erasing this by the way. To find the inflection points, it's pretty straightforward. Alright, we have to make sure that f double prime x is equals to 0. Okay, so therefore we would have here 2 e to the power of negative x minus 4x e to the power of negative x plus x squared e to the power of negative x, okay, equals to 0. So we'll have two options, e to the power of negative x and 2 minus 4x plus x squared equals to 0. okay, and obviously it'll only allow us to have this x squared minus 4x plus 2 equals to 0, okay, because the thing is, when you have something of 1 to e to the power, sorry, 1 or anything, okay, if we have, let's say for example a for example a is just something over e to the power of x equals to 0, right? The only way for this to be true is if a is equals to 0, right? So that's the logic behind that. That's why I only accepted the quadratic formula. So in this case, what will we have? What will be our x? Okay, so let's have a look first. So equations of function, polynomial, degree 2, 1, negative 4, and 2. So we actually have, interestingly, 2 inflection points, okay, which are lying along, one of them is pretty large, by the way, so it's about 3.414, okay, and another one is about 0.585, so we have 2 inflection points actually, interestingly, 0.586, okay. If you want to write in the perfect form, it's actually 2 minus root 2, okay, and this one in perfect form would have been 2 plus root 2, okay. So we have 2 inflection points, okay. So without further ado, let's sketch the graph. I'm gonna have to erase all of this because we need some space. Alright. Okay. Okay. So we're gonna sketch the graph real quick. So it would be something like this. Okay. So we know that 0, 0 is the minimum. So I'm gonna of course have a point at 0 and 2. Right. So this is 2. This is our point here. 4e to the power of negative 2. So 4e to the power of negative 3. 4e to the power of negative 2 would be. Okay. Interesting. 4e to the power of negative 2 would be 0.541. So and then here, okay, our inflection point will be 2 minus root 2. And our second inflection point will be 2 plus root 2, okay. So there might be more than one minimum and maximum, but that is not our concern, so we're just actually just plotting whatever we're given with. So let me see first. 2 minus root 2, what would be the y-axis? E to the power of, sorry, so it's gonna be less than that actually. It's like somewhere here, 0.191, okay. And how about 2 plus root 2? So let's have a look here. So 2 plus root 2. Oh, okay, it's much lesser than that. It's about 0.384, okay. And I think for 4e to the power negative 2, I think it's best if we give it in the decimal form, which would be 4e to the power negative 2 would be 0.541. Oh, okay. Okay, so I'll probably put a maybe here, I guess, 0.541, okay, to make it easier. Right, so when we are actually plotting the graph, okay, or when you're doing like a rough sketch, so we take the points which are obviously minimum maximum. This is like the most important thing for us, right? And we plot the graph. So I'm going to start sketching from here. Okay, so minimum, maximum, and maybe the inflection point, and just maybe we do not know where the graph is going. Okay, so we're gonna probably cut off at this region, by the way. Yeah, we're gonna cut it off at this particular region, okay, because we're not going to go that far actually in terms of plotting the graph. Okay, so this is just a very generic idea of how to sketch the graph. So hopefully you guys will get an idea on how to be doing this kind of problems. Now let's go for actual optimization problems. All right, so let's actually go for some optimization problems, because that's also what we were trying to discuss in today's tutorial. So let's go for that. Okay, let me erase it, make it a bit more bigger. Okay, so now let's go for an optimization problem. So we have a can here. Okay, let me just draw this can, a cylindrical can. Okay, and this can, okay, we know that the volume of this particular can in question is 500 ml, okay, which can also be written as 500 cm cube, okay, and it has a diameter, okay, which we'll call it as D, and the height of H, okay, the height of H, right? And basically it's made from this particular sheet metal. Okay, so we have a sheet metal right here which wraps around the whole can also, and as well as we are considering the top and bottom part as well. Alright, so top and the bottom part also be considered in the can. It's a whole solid can, and this is just basically the net. So this is gonna be in terms of D, this is gonna be in terms of H. So from this kind of sheet metal, alright, we're turning it into a can. Okay, so according to the question, they said that the area, okay, the surface area of the can itself, okay, so let me just make this a bit clear. So they say that the surface area, okay, is proportionate to cost, directly proportional to cost. And the question wants to minimize the cost, also aka minimize the surface area, okay, by finding the right D and H, actually by finding D and H. Okay, so what I want you guys to do is to pause this video a little bit and try to attempt this problem. It's a solid can, yeah, so meaning to say we of course have to include the faces. So it's a solid metal can. Okay, so yeah, okay, so assuming you guys have already paused the video and give it a try, so let's try to work out this problem together. So I'm going to erase a little bit here. Okay, so one thing we know is already the surface area is related to the cost, and we know about the volume, right? So the volume actually is pi r square h, right, for volume of any cylinder. And we can also write it as volume equals to pi d over 2, right, the diameter over 2 for radius squared h, and can be written as pi d square over 4 h. So our volume is 500, so 500 pi d square over 4 h. Therefore you can express the h as simply 5 times 4 is going to be 2000 over pi d square. Okay, so this one equation I want to keep. Then of course if we're erasing all this, we are going to write the surface area equation. So the surface area equation is like this. The surface area equation is just 2 pi r square plus 2 pi r h. Okay, and we can write it like this as just simply 2 pi d over 2 squared plus 2 pi d over 2 h. So of course this will lead to pi d square over 2 plus pi dh. Okay, so this is equation 2. Alright, and if I were to substitute 1 in 2, okay, what we'll end up having is our surface area equation will become pi d square over 2 plus pi d, okay, pi d over 2000 pi d square. Okay, so of course if you substitute it out and you simplify this problem, you are left with d, right? So I'm gonna be erasing all of the other stuff actually, so that will be easier for us. Let me try to erase this. Okay, yeah, I'll erase this a little bit lah. So as I'm erasing it actually, because I need some space, because we know we have to minimize anyways, so therefore we're left with our, oops, sorry, let's just go to yellow. So we're left with a equals to pi d square over 2 plus 2000 over d. Okay, and we know that the cost is directly proportional to area itself, right? Direct proportional. So we can say that the cost is just equals to k, where k is just some constant, and you have the equation, right? There'll be pi d square over 2 plus 2000, and I'm going to write it for ease, d to the power of -1, okay, to make it more simpler. And we're going to erase all the other unnecessary stuff here. Okay, we don't need them anymore. Okay, so with that being said, we're gonna take the derivative, the first order derivative, so dc over dd. Please don't be confused. So the k is just a constant, okay, we leave it as it is. So it will just become pi over 2 times 2d minus 2000 d to the power of -2. Okay, so we're of course left with what? We're left with pi k d minus 2000 k d to the power of -2. And if you want to minimize or maximize the cost, in this case we want to minimize, so we have to find the derivative. The first order derivative must be equal to 0 in order to minimize the problem, right? To find the minimum value. Okay, so therefore we're left with pi kd minus 2000 kd to the power of -2 is equals to 0. So again, we're going to erase the other side just to make sure of space. Okay, excellent. So of course we can remove the k, right? We can easily get rid of the k itself because k is just simply a constant. So we're left with pi d minus 2000 over d square equals to 0. So if I multiply the left hand side, okay, if I multiply the left hand side itself, okay, the LHS, alright, with if I multiply this with d square, okay, if I multiply this d square, and of course the right hand side itself RHS with also d square. Of course the right hand side with d square, you multiply 0 becomes, well, 0, so it's not a big deal at all. So you'll end up having pi d cube minus 2000 equals to 0. So of course we'll have pi d cube is equals to 2000. Okay, and eventually if you try to solve this problem, let me see, I think I'll probably have to erase I'm going to erase this part anyway, so I'm going to erase this part, okay, for the sake of space. So we'd have d cube is equals to 2000 over pi, which will obviously lead to d cube rooting, right? If you cube root, your value would be 2000 over pi would be 8.603. So you'd have 8.603 centimeters. Okay, so this is your value for d. Then how about the value for h? So remember that we found that pi d square over 4 times h was equals to 500, right? So we already got the value for d, we just plug it in, so we become pi times 8.603 squared over 4 times h equals to 500, and therefore h would be equivalent to do all the calculations. Okay, this is for d, by the way. So you just simply you do the substitution calculation for will be this 8.602. So your h would be 8.602 cm. So your h and d has to be roughly similar, actually, meaning to say that your value for h and your value for d have to be roughly similar in order for you to minimize the cost. So this is the first optimization problem. It wasn't too bad, you know, but you just have to know what calculations need to be used. Okay, so let's go to the second optimization problem. Let's try to tackle the second optimization problem before we end this series, right? Okay. So this optimization problem was talking about a underwater cable. Okay, so we're talking about underwater cable. Let me just draw in blue color to represent the sea, and we have this cable, okay, which is in yellow. It's going underwater. Okay, so it's an underwater cable. All right, I'm gonna call this as a underwater cable. Okay, so the underwater cable, and basically the ratio of the radius to the course, the radius, actually, you see this circle, right, we're talking about here, this circle, okay, has a radius, right? This radius is r. Okay, this radius r of the core to the thickness of the sheet. Okay, so meaning to say, if I were to draw this outer layer, okay, and this outer layer, if you measure the outer layer, this is the thickness itself. Okay, so it's saying that the ratio of the radius to the thickness of the sheet, okay, is denoted by a variable which you call as x. Okay, is denoted by x. And another thing we need to talk about is the speed at which the the transmission is transmitted across the cable, across the underwater cable, is proportional. Okay, so this speed is proportional to x square ln 1 over x. Okay, it's proportional, directly proportional, by the way. So this is directly proportional. All right, and now the question wants us to show that the relationship between the speed and this ratio of radius to thickness, okay, so dv over dx is equals to k x times 2 ln 1 over x minus 1. So they want us to show, okay, the show, it's kind of a show question to verify that we get this. And once we get this, they want us to find the stationary values of v. Okay, find the stationary, meaning to say the max and min values, find the stationary values of the function v itself. Okay, remember that the v is actually directly proportional to x, right? X squared plus ln x ln 1 over x. So of course from here you need to create a function, actually. So we need to say to create a function. Create a function of v in terms of x. Okay, so the question wants you to find the stationary values of v also, first to show, and then of course to find the stationary values. And of course also another last show question, show that the speed is greatest, okay, x equals to 1 over root e. Okay, so they want you to also again show. So there's actually three things, so I don't want you guys to get confused. The first thing obviously is to show we managed to get this derivative relating to dv over dx. This k, by the way, is just a constant. There's no need to worry, it's just a constant. Okay, and then they want us to find the stationary values itself of the velocity v. Okay, and the last part is to show that the v is the greatest at this particular ratio x, where it's just simply 1 over root e. Alright, and we are already given the relationship is a directly proportional relationship between the speed v and of course the ratio of radius to thickness. So x is basically what is just ratio of radius to thickness. Okay, radius to thickness, actually not of thickness, radius to thickness. Okay, so hopefully I give you guys some time to pause and try to digest the information. Okay, there are three things we need to find: number 1, number 2, and number 3. And of course, try to tackle the problem. Okay, so assuming you guys have paused and give it a try, let's try to solve this problem. Let me erase all the unnecessary things. Okay, I'm going to erase the question as well. Okay. So the first step obviously is to create the function. Okay, so I'm going to create the function. So it's very simple. Since it's directly proportional, we can say that v is equals to k x square ln 1 over x. Okay, there. And k is obviously just a constant, right? It's a constant itself. It's can be any number. Alright, so they want to find dv dx. So how do we find dv dx? Actually, it's simply just product rule. Okay, you have product rule here. Alright, this is gonna be a u. Okay, let me just erase this out real quick. Okay, make it smaller because we need some space. Yeah, okay, cool. So this is our product rule. This is gonna be a u, and this one's gonna be our v. Okay, so we're gonna use a bit of product rule, and I also noticed that we might have to use a bit of chain rule here. So this part I had to use a little bit of chain rule. Okay, the modified chain rule that we talked about, out and in, right? Out and in. Okay, so let's try to solve this together. The k is a constant, so don't worry about it too much. So just simply be ln 1 over x, okay, from product rule, times u would become 2x plus x square u, and then the derivative of v. So it's just simply 1 over x times, you take the differentiate or derivative of 1 over x would become what? Would become negative 1 over x square. Okay, so let's try to simplify this problem. So we'll have here k, right? We will have here 2x ln 1 over x, okay, plus x square, okay, x square, what else? So 1 over x would be how much? It would be x multiplied by negative 1 over x square. Okay, so again it would be just k 2x ln 1 over x. Okay, and we can see that this x square will be out, so it become just 1, right? So you'll be leaving with minus x. Okay, and simply we can just take out the x. It will be just kx equals to 2 ln 1 over x minus 1. So we've already managed to show, we managed to show the first part, so it's already shown. Okay, we've already proved it. Okay, so we already found the derivative. Now we try to do the second part. The second part is asking us to find the stationary values. Okay, to find the stationary values, it's quite simple, right? It obviously dv over dx has to equals to 0, right? To find the stationary values. Okay, to find the stationary values, dv over dx equals to 0. So it is just simply kx bracket 2 ln 1 over x minus 1 is equals to 0. So the first part, we take the kx equals to 0. So that means that x is equals to 0. Okay, so that's one stationary value. If x equals to 0, then your v, your velocity would be what? Your velocity would obviously be equals to 0. Right? Because you substitute 0 into the original equation. If you substitute it here, let me just show it green. You substitute to x 0, it become everything will become 0, right? But actually there's a problem. It's not gonna be 0. I have to apologize, yeah, because I realized that we have that if we substitute, yeah, you will get here. Oh, sorry, let me use in orange, yellow color. I realized that if we have v, where of course k you multiply with 0, but you have ln 1 over 0, so this is gonna be impossible to solve, right? This is gonna obviously be infinity, right? And of course there's no such thing as ln infinity, doesn't exist, right? So we have to reject this answer. Okay, so you cannot have this answer right away. X cannot be 0. Okay, that's the most important thing. If you want to have a solution, x cannot be 0. So of course there is no solution, so therefore we take the 2 ln 1 over x minus 1 is equals to 0. Okay, so we have 2 ln 1 over x equals to 1, then ln 1 over x is equals to half. Okay, so 1 over x is equals to e to the power of half. Okay, and x is equals to 1 over e to the power of half. In other words, e to the power of half can be translated as e square root. Okay, so that's the other equation, other stationary value. So the other stationary value is this one actually. Okay, because this cannot be a stationary value, it's already rejected as we mentioned earlier. So this is the other stationary value, right? So that means that your v would be how much? If x was equals to this. So let me erase this first. So let me erase this one. We can have 0. So in this case, our v would be k, of course, 1 over root e squared times ln 1 over x is just simply root e, right? So therefore your v would be, k is just a constant, you can forget about it, so just 1 over root e squared times ln root e. So it would actually be like this. It would be k, okay, and you would have here 1 over e, okay, just 1 over e times let's see, ln root e would be half. Yeah, it would be half in this case, which is logical. So you actually have k over 2e. Okay, you actually have k over 2e. That's basically the stationary value for v, right? If your x is this one, your v will be this one. Okay, right? So that's the second part done. Now they want to show the speed is greatest at here. Okay, how do you show the speed is greatest at here? So right, I'm gonna of course erase some parts as well. So we're gonna erase this. Okay, so we're already erasing this. Okay. So let me just write here. So x we already know is just 1 over root e, right? So that means your V you determine is just simply K over 2E, right? Okay, so that's your stationary value for V. Now, how to confirm that this is the greatest value? Well, it's quite simple fairly, right? We find the second order derivative. So to find the second order derivative is just d square V over dx square. Okay, so in this case, you know, you do the usual, right? We will take this form. Actually, I think this form's easier to do the differentiation because this is just simply a k, right? So it's a constant. In this case, I will take the k out, and then now we will have oh, okay, interestingly we'll have also, actually no, never mind, I think I'll use the final form now, it'll be easier. Okay, so we have to use the product rule a little bit. So kx times this whatever function that we're given with here, right? We have to use this one instead. So therefore it would be okay, let's do it like this. So it'd be what? So 2 ln sorry, 2 ln 1 over x minus 1 times with k, okay, the product rule, plus kx, okay, kx, and you differentiate the inner function, so just simply become 2 1 over x times negative 1 over x squared, right? So to simplify it, you end up having what? You have k bracket 2 ln 1 over x minus 1 plus kx, okay, so if we bracket is just negative 2, so you have 2x times 1 over x squared, okay, so you can simplify that a little bit more and then you end up having x, right? So therefore you can just write that d square v dx square is just k 2 ln 1 over x minus 1 plus kx negative 2 over x. Okay, so I'll just leave it for here at the moment, and I'm going to erase all these intermediate steps. Okay, so when your x is just simply 1 over root e, so your d square v dx square will be what? You'll just simply be k, right? So it's just 2 ln 1 over x minus 1, so calc is just simply 1 over root e, root e with k times 0, okay, plus, you know, you have k times negative 2. Why I say k times negative 2 is actually because I didn't simplify this part, but you know, if you simplify it'd be 1, right? So therefore you'll end up having negative 2k. Alright, so what does it mean by having negative 2k? That means to say that x over 1 root e is maximum. So it's a maximum value. Alright, so yeah, finally, so we're done with the first chapter. Alright, from basic differentiation until optimization, and I hope that this video has been really helpful, this this series of videos. So yeah, we'll proceed with the other chapters also, and thanks for watching. So thanks, see you guys next time.